Welcome, everybody. I've already been introduced, so I'm gonna just start my talk. We are gonna talk about 3D images in the forensic context, and especially for identification purposes. I'm gonna start with an example. A common technique in anthropology is facial comparison. We are given two photos, and we want to check whether the subject is the same person. There are a couple of things we can do in this moment. We can do like more analytic comparison, like trying to compare the face as a whole, or a more detailed morphological analysis, trying to analyze each trait of the face and maybe compare against an atlas. Given that in these two photos there is the pose is different, we cannot use measurements. We cannot measure, for instance, the width of the face compared to the height, because the pose is different, so the measurement will not look the same. Also, we cannot do a superimposition, meaning that we cannot overlay those two faces to have a better look at the difference between them, because given that the pose is different, that wouldn't work. We will not get a good overlay. Instead, if you can get your hands on a 3D model, or you can scan a 3D model of this person, then with a 3D model and some work on your part, you can perfectly align the 3D model with the photo, like we are seeing on the right-hand side. And when you make a good overlay, then you can make a very detailed comparison, and you can be very precise. So that's a motivating example for using 3D images instead of 2D images. Okay, so what we are looking at is a technique called superimposition that can be used in several tasks. Here we can see 4 examples. We already talked about facial comparison. There is when we are comparing two pictures of a face. Then we have craniofacial superimposition, which is when you are comparing a skull that has been recovered with a face in a picture, in an ante-mortem picture of a candidate. You can apply the same principle to radiography. So you can have a 3D model of a bone, for instance, the clavicle, and you can overlay it on top of a radiograph. And finally, you can also do that with a dental scan. So you have a 3D model of the teeth of somebody, and if you have a picture when the teeth are showed, you can then overlay them and compare, right? So technically, this is called 3D to 2D superimposition, which is the task of overlaying a 3D model of an object on top of an image of another object, but you have to match the pose between the two objects. Of course, it's not just displaying the 3D model on top of another. You need to match the pose perfectly. So talking about applications, we already mentioned them: facial comparison, craniofacial superimposition, delta comparison, and comparative radiography. So what does it take to make a superimposition? So the idea, of course, is to show a 3D model on top of a picture. But we are not just displaying a 3D model in any way. We need to do it in a realistic way, like we were taking a picture of the 3D model through a camera. We can see why in this example. Those two pictures show a lot of perspective distortion, especially the one on the left. Okay, so what you are seeing, the shape of the face is quite different. For instance, we can see that the nose is pretty big in the left-hand picture, and it's smaller in the right one. And I can assure you there is no way that by just simply moving and rotating a 3D model, you can deform it like that. Okay, so the idea that you can do a superimposition in Photoshop doesn't work because you cannot control the perspective distortion. You're not displaying the 3D model in a realistic way. You are displaying it like in a 3D editor, which is not what happens when you're using a camera. So the key fact here is that we need to take into account how a picture is taken. Making a superimposition is basically reproducing a photo, meaning that we want to produce the same photo by replacing the subject with our 3D model. And to understand that, how that can be done, of course, you could do it in principle, and it was done like that many years ago. You can use a real camera and a real object, but that takes a lot of time. It takes a lot of trial and error to adjust everything. It's much easier if you do it inside a computer with a 3D image or a 3D mesh. But the essence is the same. So now I'm going to list a feature of a camera that are called camera parameters and see what is the effect on the picture that you get. These parameters come from a mathematical model, which is maybe sound more complicated than it is the pinhole camera model, which is the most basic camera model you can get. It's just like the camera obscura, where an image is formed by light rays coming through a small aperture. In a regular camera, instead of the aperture, there is a lens, but the essence of how a camera works is the same. So the pinhole camera model, although it's not perfect in some very precise context, is not enough. But for superimposition and many other applications in software engineering, is definitely enough. Okay, so we were gonna use that model. This is the list of parameters that are relevant when you are taking a picture. Obviously, there is the position of the 3D model, there is the orientation, and then we have three more complex parameters. Maybe the first one is not that complex, is the focal length. Let's start with that one. Okay, so focal length is simply the focal length of the camera. Sorry, of the lens of the camera. You're gonna, if you have an expensive camera, you're probably gonna see it written on the lens. It's usually expressed in millimeter, and typical values are between 18 and 300. What does focal length does? It determines the field of view, so the angle of view. And it works like this: the larger the focal length, the smaller the angle of view. So colloquially, we could say that it zooms more. Okay, you can get closer, although that's not really how I should explain it. You will see why later. I think this picture of me clarifies pretty well. And I want to mention that in digital photos, you can check what is the focal length of a picture by checking the EXIF metadata. Usually digital pictures have metadata, and focal length is one of them. Next, we have subject to camera distance. This is simply the distance between the camera and the subject. It goes without saying that if you are taking a picture of somebody and you get closer, well, the subject gets bigger in the picture, right? But there is another thing going on, which is perspective distortion. if you get very close, like the typical example is when you're taking a selfie, you will notice that the shape of the face becomes unnatural. We can check out the image at the bottom of the slide. If we start on the left side, we can see that the face of this person looks pretty nice. And as we move to the right side, we see the typical effect of perspective distortion, which is the nose gets bigger and the ears get smaller. This is because the nose is relatively much closer to the camera than the ears. And that's going to happen with not just with a face, but with any object. This is the effect of perspective distortion. Okay, so we mentioned focal length and subject to camera distance. So we can use either of them to change the size of our subject in a picture. That's really intuitive. When you're taking a picture and you want to make your subject bigger or smaller, either you move or you use the zoom, right? Okay, the relevant thing here to understand is that if you use your zoom, you're not going to change the amount of perspective distortion. But if you move and if you get very close, then you're going to introduce perspective distortion. That's not an issue per se. Well, if you like nice portrait of your spouse, for instance, you should get far and use the focal length adjustment. So use the zoom. But beside that, for what we are concerned with superimposition, it's not a problem that a photo has perspective distortion, but it's important to understand why and how do you get to that effect. And finally, there is another parameter which is a little complex, and it's called the principal point. To understand what it does, we need to look at what happens when you crop an image. Here there are two images of me. I'm talking about the top row. And I was standing more or less at the same distance from the camera, but in the left picture, I'm in the middle of it, more or less. And in the right picture, I'm in a corner. And if we zoom in on the face, we can see that the shape of the face is quite different. This is because perspective distortion acts differently if the subject is on the side of the picture. So this is, in itself, this is not a problem. If you reproduce perspective distortion correctly, this will fix itself, meaning that the 3D model will have the same distortion. But now what happens if somebody, the person that gave you the photo, cropped it? Well, then we don't know that the picture has been cropped, so the system doesn't know that that face was supposed to be in a corner, right? So so the 3D match is not deformed in the same way anymore. I'm talking about the picture on the left. Well, that's a problem because the superimposition is not correct anymore. They're not gonna match. This can be fixed by changing the principal point, which is another parameter of the camera model, and that can reproduce the kind of distortion, which I'm calling here the corner distortion, but it's actually perspective distortion. It just happens in a corner. So the lesson here is that, is it possible to work with crop images? Yes, but it's more difficult because you need to compensate for an information that you have lost. So this provides an argument for using original picture always. Okay, so that concludes the part when I'm explaining how to get a superimposition. Obviously, this is more of theory about it. I'm not showing our software, which is specialized in making superimposition and overlay easily. But those are the parameters and the things that you have to keep in mind when you're trying to make one. What I just explained can be applied to facial comparison and also to dental comparison. I mean, it can be applied to the superimposition in general, but there are two other techniques which are kind of facial superimposition and later comparative radiography, which requires a little more effort and explanation on my side. So next, I'm gonna talk about kind of facial superimposition. So the basic ingredients are the same. We have a 3D model and a picture. The 3D model is that of a skull, and the picture is an ante-mortem photo of candidates. And we want to create an overlay between the 3D model and the photo. The thing is that now the two objects are not the same. There is a skull and there is a face, which are very similar in a way. I mean, geometrically, they are quite close, but they are not the very same object. So we cannot expect to be able to look at the overlay and check and see immediately if the superimposition is correct. In our heads, we need to take into account that the surface of the skull is covered with a layer of soft tissue that basically made up the face. So to make our life a little easier, what it's usually done is to take into account craniofacial landmarks. These are reference points that can be located on both a picture of a face and the mesh 3D image of the skull. And we know that if the superimposition is correct, those points need to align. They do not align exactly. We need to take into account that they are separated by soft tissue, but there are ways to take that into account. Here is an example. I mark the landmarks on the picture and on the 3D model. The image on the left would be a very bad superimposition with no overlap at all. And the image on the right would be a good superimposition. We see that the landmarks do not overlap. Well, not all of them overlap exactly, but if we take into account those little arrows that represents facial soft tissue, then they overlap. Okay. Okay, so we added one more technique, and now we're going to talk about comparative radiography. Again, basic ingredients. We have a 3D model of, it can either be a bone or a cavity. I'm mentioning cavities because, for instance, there are frontal sinuses that are part of the skull. They are not technically a bone. They are a cavity inside the bone, but their shape can be used to identify somebody. That's why I'm mentioning cavity. But think of a bone. Then we add a radiograph, and what we want to get is an overlay, right? Overlaying the 3D model on top of the radiography. There is one thing to take into account, is that while in the radiograph we can see inside the bone, literally, we can see, for instance, patterns in the density of the bone. We don't have that information in the 3D model, because the 3D model just represents the shape, the external surface. So we don't know anything about what's inside. That's why when we make an overlay, we need to think only of the shape. We cannot overlay the bone using also information about the inside, just the silhouette. This is well, an explanation of radiography. Well, in case you don't know, how do you get an X-ray radiograph? Well, you place a sensitive detector, which is sensitive to X-rays. You put it, for instance, below the arm of the subject, and then you put on top an X-ray generator. The rays are are emitted by the generator, and then sorry, they are absorbed by the tissue that you are exposing. The thicker is the denser is the tissue, less rays goes through, and then you get an image which is lighter. Now, the important thing here is that despite you cannot really see inside an object with a camera, if you just look at the shape that you can see in a radiograph, they are not that different from what you can get from a camera. Let me explain. If I take a 3D model of my clavicle and I take a picture of it and I just look at the shape, I can get the very same shape by taking a radiograph of my clavicle. Of course, you need to match the pose, but you can get exactly the same shapes. There is no like special kind of shape that you cannot get with photo or radiography. They are the same class of shapes. And also it can be with some equation you can work out from your radiography setup. You can work out where you need to put the camera to take a picture of the 3D model to get the same shape. So given this idea, you can more or less forget that you're working with radiography and think about taking making an overlap with a 3D model of the bone, even if your picture is actually comes from a much more complex process, such as radiography. But fortunately, you can see it that way, and it makes easier. So with that in mind, everything I said before applies also to radiography, right? So the same camera parameters apply to overlapping 3D models of bones on top of radiographies. Okay, so this is the first part of the talk. Now we are going to look at techniques to actually acquire 3D images. This is the same thing as saying scanning technologies, 3D scanning technologies. First of all, a little overview of 3D models. What is a 3D image or 3D model? Well, there are two kinds of 3D images. The one that we see at the bottom are called volumetric images. These are usually acquired in the medical context. And well, the one I'm showing you, it comes from a CT scan. But if you look at MRI, for instance, magnetic resonance imaging, you will get a similar kind of image. You can think of these as a series of images, a series of slices that can be along any directions. So that's a 3D image, and you can actually see what is inside. Okay. This is in contrast with what you get with a mesh. A mesh is just a set of polygons, so it's a surface, like the skull we are seeing at the top. And the skull just records its shape, and on top of this shape, we can add a texture, which is just an image, and this image records the color and other properties of the material, like such as how shiny it is. Okay, but we don't get information about everything that is inside the surface, right? So what I said so far applies only to 3D models, so 3D meshes, not volumetric images. Although if you have a volumetric image, such a medical image, you can usually easily get a 3D mesh. Like for instance, in the bottom image, you can segment, you can highlight the skull, and from the volume of the skull, you can get a 3D mesh. Okay, So beside the method I've just mentioned, there are two technologies that can get you a 3D model. And these are structural light scanners and photogrammetry methods. Let's start with the first. A scanner is it's a small device which usually includes camera, usually two of them, and light emitters. This is not a regular light emitter; it's a structural light emitters which does kind of emits a light with a pattern. And how do you scan? Well, it's very similar to what it's shown in this image. You held the device in front of the object you want to scan. In this case, is a skull, and then you're using a computer, and the software gives you a preview of what has been scanned so far. So if you're scanning a skull, you're gonna see part of the skull being appearing on the screen. And using that information, you are able to know, for instance, that you miss something, or that you're being scanning the front of the skull but not the back. And you just you need to hold the scanner to the right distance. Also, the software is going to warn you if you're not doing it. But that's the idea about 3D scanning with this kind of technology. Pros and cons. Well, pros, these systems are usually easily portable. They are easy to use. The scan is pretty fast. I reckon, for instance, 15 minutes. After the scan, there is a post-processing phase, which is usually quick, half an hour. Maybe you need to clean the mesh a little bit manually and leave the computer running for a little bit, but it's not that long. You can scan objects that have different sizes. Like, for instance, the same scanner could be used for a skull and for a car. You don't need an especially powerful computer. The precision you get is decent, 1/10 of a millimeter, which in this context is not very precise, but it's enough for a lot of applications. And another advantage is that you don't need so much training. Usually, after an afternoon trying to scan, you get the hang of it. The cons are that the texture is not that good. It's usually not photorealistic. It's still gonna look okay. You're gonna see right colors, but it's not going to look like a photo. You will not get confused and think that that's a real object, completely real object, as you will get in a picture. But the main disadvantage is the price. Typical range would be 7,000 to 30,000 euros or dollars. This is in contrast with photogrammetry systems. Photogrammetry system comes in many ways, but the essential elements are cameras with the lenses, cables, tripod, lighting system, which can be very simple or very complex. And then you have things like a rotatory table, stands, cables, computers. Well, not computers. I'm going to explain better. With this picture, we see two very different systems. On the left side, there is a very professional system with tens or maybe hundreds of cameras, which need to be connected and synchronized, and you get expensive equipment to get maybe 100 pictures at once. This is used, for instance, to scan an actor for special effects. And on the right-hand side, you can see a rig that I've used with just one camera, 3 flashes, which could be even replaced with regular lights. And so you can see there is a lot of difference in both the price and the complexity of those systems. For instance, the system on the right, I mean, it's easy to use, and it's pretty simple to set up. That's why I called it a simple and cheap setup. These are the kind of photos that you get. Pros and cons. Well, the first pros that I mentioned is the price, because if you are using just one camera, you can maybe start with 1,000 euros. You get very high quality models, and you get very high quality texture. Actually, texture that look like a real object. What are the cons? Well, one is that the system is not easily portable. It's much better if you have a dedicated room or dedicated part of the room to scan. You need a powerful computer with dedicated graphical processor. That's probably not an issue nowadays, but you still need it. You need some training, because you need to be able to take picture that are right, that looks good, that are sharp, and when you don't, you need to understand why and fix it. Once you do that, you can get scans relatively quickly. After that, the post-processing is long. Well, maybe 1 hour, for instance. You don't need to work on the computer, but you need to leave the computer working, which can be a problem when you need to scan a lot of bones, or you make a mistake, and on top of the time you wasted taking a picture, now you left your computer running for 1 hour, and you need to start over, right? Okay, but those are the two main alternatives: structural lights and photogrammetry. Depending on your situation, one could be better than the other. Nevertheless, I wanted to add to the presentation some common issues you could detect on 3D meshes, so you are aware of them and you know how to fix them. Well, the first one is noise. You just simply see extra surface that is not part of the object. This is a scan that it cannot be used because there is a lot of extra material, which is probably random. Another one, which is more subtle, is the lack of details in the geometry. This is, for me, it's the first thing that I check when I handle a 3D model. We can see that this 3D model looks very good. If you look on the left, it looks very good. It looks photorealistic. But if you remove the texture, you can see that the shape of the model is not really detailed. For instance, inside the nose area, it's not really a hole like it would be in reality, and like you would think when you look at the texture. And that's an issue, because then you cannot measure anything inside the nose, for instance. Next, well, your model could lack detail in certain specific area. I've already mentioned like the area of the eyes and of the nose, which is especially important for craniofacial superimposition. Then there is simplification. Usually 3D scanners provides you with models that are very big in terms of size, in storing size, like megabytes and gigabytes. That's a problem, because it usually gives you a model that has so much details that these small details are actually random. They are not actual detail that you can see in the object. So you are wasting a lot of time waiting for your program to load to use these very big files that you're given, and they don't really contain any useful information. So so sometimes you need to simplify the sculpts. Every 3D scanning software will provide this feature, but you need to know that you need to use it. It's called simplification, and it will greatly reduce the size of the meshes that you are producing. Of course, you can also do it too much, so you can have an excess of simplification, so you are gonna lose all the detail in your model, so you should avoid that. And finally, when you're working with a 3D model, you should also check that there are no gaps. Like in this case, the black areas are not something that was black. They are places where the scan didn't work, and you are left with holes everywhere, especially in the teeth in this case. So that's also a common issue, and in this case, you cannot use the scan if you want to actually take into account the teeth. Okay, so after looking at possible problems with 3D models, I just want to mention a couple of possible issues with images. Images are, of course, much more familiar to everybody, but nevertheless, there are common issues that could occur. I already mentioned that you shouldn't crop images. Another possible issue is getting rid of metadata. Metadata is very useful. Here I'm showing you some of the information you can find in a digital picture. Those are called EXIF metadata, and you can see, for instance, the time the picture was taken, what camera was used. You can see the focal length, and in this case, from the focal length, which is supposed to be 2 millimeters, I can tell that's not a realistic value. No camera will get you a photo with a focal length of 2 millimeters, and that's gonna tell me that this picture had been cropped. Okay, so that's very useful. Sometimes you get even GPS coordinates, which are obviously very useful. And for instance, by checking the modification time and date, I can see that this is different from the creation of the picture. So probably this photo has been edited. So lots of interesting things in the metadata. And that's why you should be careful to keep them. So how do you lose them? Well, one way is to, for instance, send this picture through social media platforms such as WhatsApp, Facebook, and others. They usually reduce the quality of the photo, and also they eliminate the metadata, which in our case it's an issue. It's probably good that they do, because in everyday communication you don't want to send this information everywhere, but in our case it's a problem. What can you do? Well, you can use email. Email doesn't do that. So if you're sending a picture to a colleague, or a victim is sending you a picture, just tell them to use email. With respect to analog pictures, you should, if you're going to use it in a software like ours, or you want to store them, you should really invest in a proper scanner. Like, even the cheapest photo scanner is going to be better than the alternative, which a lot of time is just taking a picture of the picture, like pulling your camera phone from your pocket and taking a picture. This is gonna obviously reduce the quality of your analog picture a lot. And also, if you don't keep your phone in the very exact best position, you're gonna introduce a distortion like the one you are seeing on the right side. And that will distort all the picture. Like, for instance, in this case, the background, the frame of the photo is supposed to be a square, but it's not anymore. And you will also create confusion with the metadata, because I'm on somebody like me gonna get this picture, and it's gonna say that this was taken this year by a mobile phone, and I can see that this is an analog picture that has been scanned. So those are my, sorry, I got back. Those are my recommendations for handling this data. And now the last part of the talk is about automatic superimposition. Well, what I've explained before about camera parameters and how to perform a superimposition, those information is supposed to be used to make manual superimposition, right? I wanted to mention that our software has been designed to facilitate manual superimposition. So it gives you tools that are expressly designed to make the whole process quick, easy, and reliable. Okay. Nevertheless, in cases you are making a lot of superimposition, for instance, because you are comparing a skull against many possible victims, or in any case where you have a lot of candidates, making a lot of overlays of superimposition can be very time consuming. That's the motivation for researchers like me. Actually, that was one of the topic of my PhD, was automatic superimposition, but it's not just us working on this. There is a large community of computer scientists working on this kind of projects. So we were investigating solution to have them automatic. Okay. Let's review how these are done. So the process is known as camera calibration. When you are making a superimposition, you are trying to reproduce a photo. So you are trying to find out the camera parameters. And this problem in computer science, in computer engineering, is known as camera calibration. So the typical approach is that you use landmarks, corresponding points that you can locate on the picture, and you can locate in the 3D object. And the principle is that your landmarks need to overlap. That's how a computer can solve this kind of problem. So technically, well, you can write some equation that connects the position of the camera, the orientation, and the focal length to the position of the landmark. And you know that you want your landmarks to overlap. So you can solve this system of equation. Again, in a computer, you cannot do it by hand. It wouldn't make sense. I cannot do it, definitely. Maybe you can. So by solving this equation, you get the exact camera parameters to get an overlap of the landmarks, right? So that's everything we want. So now if we want to overlap automatically a face, well, we need to mark the landmarks in the photo and in the 3D model. And after a very quick processing time, which is like less than 100 of a second, so you know what, you're not even gonna notice it. Well, you get a perfect superimposition, like we can see on the right-hand side. And in particular, we see that the landmarks overlap perfectly. Okay, so that's easy. That applies to facial comparison. You can also do it with dental comparison if you're able to mark areas of the teeth that should match, right? But in case you want to apply this to craniofacial superimposition, there is a few extra tasks that you need to do. Well, we already mentioned that the key aspect of craniofacial comparison is that you are comparing a skull and a face, which are different, and this is reflected over landmarks. Skull landmarks are not the same as facial landmarks. The difference between them is, of course, the facial tissue. The good news is that you know what is the direction of these facial tissues. So you know that from the surface of the skull, you need to move, for instance, forward by a few millimeters. And actually, the thickness of facial tissue has been studied extensively by anthropologists, well, physical anthropologists, and you can find, and we actually provide them with our software, populational study that tells you, for instance, the average soft tissue depth of Caucasian person, right? So that's what we do in the software. We estimate the position of facial landmarks, starting from the cranial landmarks that are corresponding to them. And then we add a vector, which is the thickness of the vector, is the average thickness of soft tissue. And the direction, we use the direction of the soft tissue again. So in practice, this will look like this. Well, we mark again landmarks on the face. We mark landmarks and vectors of the soft tissue on the skull. We apply our system. We estimate the landmarks, and again we get automatic superimposition. That's great because performing a superimposition on a skull and a face, it's a little more difficult than just two faces, right? So that's great that we found a way to have this done automatically. And finally, I'm gonna present how superimposition can be made automatic on radiographies. In this case, well, we already mentioned that you can think of this as superimposition over a photo, but the information that we are going to use, it cannot be based on landmarks, and instead we are going to use the silhouette, the external shape of the bone. So the first thing that we need to do, instead of marking landmarks, is marking the shape of the bone that we want to use. In this case, is the clavicle. So that's what I've highlighted in blue in this radiograph. And then you can start projecting the 3D bone on top of the picture. And we can see that in this case, there is no overlap at all. But if you adjust your camera parameters a little bit, you can get maybe this. This is a slight overlap of the two. And as I mentioned, what we are going to use is just the silhouette. So I want to forget that I'm working with a radiography and that this is actually a 3D model, so you can see a little bit of the shape. So let's go to this. And then now I want to measure how big is the overlap. So I draw this in green color, and we can see that, well, there is some overlap, but we can do much better. Maybe we can try other camera parameters. So what I've just described is the process, which is called, well, technically an optimization process, which is like it goes through a loop. You start by choosing some camera parameters, you apply them to the 3D model, you relay them on top of the radiography, then you find out what is the common area, you calculate how big it is, and if it's large enough, well, you can stop. You already found a good alignment. Otherwise, you modify the camera parameters in order to increase it. So that's how it's done. This is quite different from what we were doing with landmarks. Indeed, the process with landmarks is just a computation that takes well, way less than 1 second. And in this case, it can last a couple of seconds because it needs to go through the loop a few thousand of times. That's the difference. Okay, we are almost done with the talk. I just wanted to mention before I go that everything I showed you, all the picture has been created using our software, Skeleton ID. In 2021, we launched the first version of it. You can talk with Sebastian if you want to get a demo and see in detail how everything I explained works. I just wanted to mention that, of course, with the current version, you can get manual overlay in all the fields that I mentioned. All the 4 techniques can be used manually. And you can use the automatic methods for craniofacial superimposition and for facial comparison. And we are working on the finishing touches of the next version, which will be version number 2, that is going to be ready, well, in a couple of months in December of this year, right? So that's it. So everything gonna be automatic, and you won't need to do anything by hand, hopefully. Okay. So thank you very much for listening to this talk, and I'm available for any question.